Okay, where are we? So last time we were struggling with the mid, the split, the query, right? So for example, we have um, 0 to 11, and we want to search for 3 to 8, right? So the mid gonna be 0, 5, 6 to 11, right? So 3 gonna be less than the mid, right? So we're gonna search for 05 because 3 less than the mid. And we also gonna go to the right because 8 is greater than 5, right? So that's what we need. So this will be sum equals 0, count total. If left, if mid, if left is less than mid, then total plus equal this, right? And we also gotta do if right is greater than mid, less than equal to this. We do either one work, okay? Then total gonna be plus equal this. Right? And we can cancel, right? Try this out. Okay. Zero zero. Okay, so we're looking for 1 to 2. So it should go to 01, 00 and 01. 02, looking at 1 1 and 2 2, yes. Something is not right. So 05, 02, then looking at left mid, okay. Okay, so let's do this. go to right and here. Go to right mid. Go to 2100 around here. This is LM. RM. Oh wait, I'll go to MR. So this is so before this is O2. This is what we have, O2. And it said we should go to the right. So what is the mid here? Something is not correct here. Mid is one here. So or they asking for 1 and 2, right? So right now we have, where's my pen? We have 0 to 2, and we guess the mid is 1, right? So okay, so less than or equal to mid, we let it go to the mid, otherwise, but right is also greater than mid. Let's try that out. Go to left, we got 1 1. So 1 1 is 0 1. Yep. So what is this? Got? Do we got? Didn't we? If root F equal left and root right equal right, then we found, right? And oh, see. So right now it just go here and it just crashed. Right? We found the one here, and then it just end. Right? So left right value. Something we set up is wrong. Okay. One, one, 4 here, right? If root dot left equal left, or we go 0, 1, and we go to 1, 1, yeah. So we go to 1, 1, yes, we found them, right? If oh, guys, okay. So this is correct, but this is still 0. At 1, 1, we could be looking for number 4, right? So we got 0, right? We should have got 1, right? So the 2, 2, yeah. So 2, 2 is 4 is 1. Mid equal to why does this not work? So left right is this one. So it go from right here. Go to MR here should go to 2, right? Greater than 1, 2. Oh. Right. So 1, 2, it go to 2 here. Mid 2, go to 1, 2. And oh, it didn't find it. Right. So something is wrong here, okay? So we're looking for, we are at O2. We are looking for 1, 2, right? So the mid of O2 is 1 here, right? So we say that, okay, something wrong here. So we want it to look at 1, 1, right? And then the 2 here also greater than mid, right? 2 here greater than mid. Then yeah, 2 greater than 1, yeah. So go to MR. So this is, we have to do 2, 2, right? Because it's always greater than, right? So oh, we have to do mid plus 1, right? Yeah. one. Let's see if we pass now. Pass all the case, then it's been nice. The print stuff here. Submit. Yes. So this one is good. Okay, so let's commit to the GitHub. Commit to GitHub. All right, and where's VS Code? Took a lot of work, but I think I understand that now. Do solution tree here. Making sure solution is working. What? It's inside here, right? Correct. Oh. 9. Oh, this is solution 2. Okay. Let's make this a new commit then. Oh, wait, forgot the horrible, but that's fine. Okay. Supplementary. Yes, just get pushed. Okay. So now we go on to Yelp. We'll have to be a largest be what? Heading one. $7,000, $11,000. This is better, but this is the best right here. Okay. All right. Let's see. Maybe we see if we can do. Oh, forgot. They also do storm, right? Yet another sample of storm is drifting to indexing order history by relating to Elasticsearch. Let me move this here. What does this do? For is okay. So we can just reference this. Okay. So that was this one. Now we look at this one. Joinery, a tale of unwindow joint. This stream is, remember, this stream is possible because of Kafka. Okay, so it looks like a Apache link. For joining stream, for aggregating data, and streams. What is this? For joining, filtering, So we have they did talk about Salesforce at some point. Yeah, right. No, okay. Mm. So 1, 2, 3 review. They mistype it, isn't it? Review content 354. Cool business 1, 2, 3. So they do a Cartesian product of all of these. So basically, different solution than using Sculpt. Okay. So some latest solution to updating. Checkpointing in RockDB. look at this. Multi-way. Look at this. What is this? Streaming. Cassandra into Kafka. So I guess it's similar to how they stream MySQL. They stream this from Cassandra. Let's see. Okay. Part 1. Yep, they just Cassandra just one of the table they use data storage they use. Similar to other DB they use. This time, Cassandra app. Stream table duality, whatever that means. I think that just means that with I think I explained in my different Substack spot that basically when you stream the data out of the table, you should be able to create the state of the table. I think that was in. Did I mention that in the Kafka post? In my post here, what they say here? Yeah, maybe we should mention about that in our post this time. What did we do? Central. Yeah, I think so. Stream table. Go ask Gemini. Stream table duality. Yep, I think that's what we should talk about that in here. Let's mention about that here. Now note stream table duality. The fact that you can stream because you can recreate the table, state of the table. Mm. Yeah, because it's a NoSQL database, so you don't know if they have all the schema, right? What? What is wrong? You're writing to both Cassandra and Kafka. No, that sounds crazy. This sounds promising. Processing commit log exposed by Cassandra change data capture. What did they use? Yep, this is what I suspect as well. They're gonna do the change data capture because it's easier. So basically, Cassandra to change data capture publisher to Kafka, right? And then finally to data pipeline. Yeah, it's the access table. Cassandra write to access table. Sort the string table, and then later on they do compact to merge the data. Okay. So all of this is provided by Cassandra. And then finally, once it enters Kafka, it will be done. Because the consumer on the other end would just get that and go wherever it needs to be. They just route to the partition key by the Cassandra. Okay. So now we go to part 2, I guess. And they do Apache Flink. It seemed like they switched from Apache Storm to Apache Storm to Flink now. Okay. Mm. Is this like Yale mascot? Is Squirrel? Yeah, once you publish the data into the publisher, whatever happens, fine. Oh, so when you set up the CDC, only data from that point on. This is similar to what? What's that? Kinesis checkpoint. Was that vertical, horizontal? Right here. So Kinesis is basically Kafka, AWS Kafka. What is the Kinesis stream mode? Horizontal. Oh, trim horizon. Yeah. Starting position. Whatever this is, right? Similar to this. When you do this, yes, just stream table duality here. You want to somehow, when you stream, you can recreate the state of the data. Okay, backfill. Okay. They have a YouTube. Let's watch this. Okay, let's see. What is this? This X. Bruh.
Yeah, thank you everyone for coming in, listen to us talk. My name is Abrar Sheikh. I'm a software engineer at Yelp. At the time I worked on this project, I worked on the data pipelines with the data pipelines group, and that group is responsible for building and maintaining infrastructure to enable microservice to microservice communication and database to database replication. Up here with me is Andrew. Andrew works for database reliability and engineering group within Yelp. They provide MySQL and Cassandra as a platform for other application developer. Andrew has a ton of experience scaling out, building infrastructure around Kafka inside Yelp. We both represent Yelp. Yelp is a platform for connecting people with great local businesses. It's where you can go to find the best business around you, make a reservation, get in line in a wait list, and even order food.
Hold on, that's crazy. What? Is that the same person? No, he's still alive. Don't know. Where is the dude LinkedIn? But let's watch.
We are here to talk about Cassandra as a source connector to Kafka. And this talk will contain design, implementation, and architectural choices that we made along the way. Cassandra is a big deal at Yelp. It's one of the source of truth databases. We use it for a lot of business critical applications like ad analytics. Our push notification infrastructure is based off of Cassandra. We use it for application caching and also tracking business and user activity feed and a lot more. We have dozens of individual Cassandra clusters deployed, and they're sharded by application. What that means is every microservice gets its own dedicated Cassandra cluster. We run a mix of 2.2 and 3.11, but that is changing slowly. We're upgrading all our own Cassandra cluster, our old Cassandra clusters to 3.11 now. A little history about Yelp. At about 2011, Yelp was a single code base repository. There were about less than 100 engineers at Yelp, and all of them were working off of the same repository, which contained about 1 million lines of code. You can imagine this quickly became a problem because we were restricted by the amount of new features that we could push out to our customers. Yelp at the time only had 2.
I don't know if mentioning line of code is actually helpful other than maybe you should refactor your code base, because that's a lot.
Two code pushes a day, so developers were strangled to get their CRs into that pushes. Naturally, to solve this problem, we moved to a more microservices architecture, wherein we broke up that big monolith into smaller microservices. Although this solved the problem of developer velocity and efficiency, this created new problems. Each of these microservices is backed by its own dedicated database, like MySQL or Cassandra. And communication of data between these microservices became a challenge. In about 2014, we had about 150 microservices. The problem of data silos can be explained well with Metcalfe's law, which states that the number of communication links in a telecommunication network is directly proportional to the square of number of clients in that network. So with about 150 microservices, we would have had about 22,000 omnidirectional communication links. We did try to chase this problem by building out REST APIs for applications to communicate with each other, and also build complex ETL pipelines to replicate data from MySQL to Redshift, and realize that this is not going to scale, and the amount of engineering we would need to put into this would have been huge. Our solution to this problem was to build a universal data pipeline. Data pipeline at Yelp is the backbone of our streaming infrastructure. It's backed by Apache Kafka. That means every data set at Yelp is kind of represented with a data stream in Kafka as a topic. All our microservices write to this universal bus, and the other microservices read off of the same bus. Producers can publish to the data pipeline stream, and consumers can read off of the same stream, hence reducing the O of n squared communication problem into an O of n problem. The expectation that all producers need to have with the data pipeline is every message that they publish need to have this message format, which contains 4 key pieces of information. It needs to have the schema ID, which is just a reference to the Avro schema that describes the data within this data pipeline message. Second is the message type, which kind of explains what kind of operation this is trying to do in data pipeline. All the create, update, and delete that you see here has one-to-one correlation to the source operation in the database. Like an insert statement in MySQL corresponds to a create message in data pipeline. It needs to have the payload. Payload represents the complete view of a row in the source table corresponding to a primary key. It also needs to contain the previous payload, which is the complete view of a row in the source table corresponding to a primary key right before an update or a delete could have been applied on that row. So that is an expectation to use the data pipeline within Yelp infrastructure. So the story so far is we built this universal data pipeline, and all microservices were able to communicate with each other using this pipeline. The next thing we did is built a source MySQL connector that replicates true change data capture messages out of MySQL into data pipeline. That means at the end of this project, we had one data pipeline stream corresponding to every MySQL table. the next thing we did was built an array of sync connectors that would replicate those data streams into one of these other databases for purposes of application analytics, information retrieval, and like table replication. This pipeline in itself was extremely valuable, and as a business, we derived a ton of business value out of this pipeline. But there was still one missing link here. At Yelp, we have two source of truth databases. MySQL is just one of them, and the second is Cassandra. So as part of this project, we built a true change data capture system that streams data out of Cassandra and into Kafka while adhering to the message data pipeline format we discussed before. In the following slides, Andrew is going to take us through the architectural and the decision choices we made while implementing such a piece of infrastructure.
All right, thank you, Abrar. So this talk is principally about streaming information from Cassandra into Kafka and doing it in the same format that our data pipeline already expects. And in this way, we can reuse all the components we've already written to process MySQL streams. So the first question is, why did we need to do this? And as we've said, Cassandra is a source of truth for many of our services. Because of that, if you need this data, you have to go to the cluster to get it. But Cassandra isn't optimized for all types of operations. Maybe you'd want to take this data and run a Redshift query on it. Maybe you'd want to ingest it into Elasticsearch. Maybe you need to join it with other data that we're already streaming or do some sort of arbitrary stream processing on it. So this is designed to sort of solve that problem. And the other thing we found is that scanning a lot of data in Cassandra can be a little dangerous. We've had clients that have wanted to see how a lot of their table changes over time, and it caused some real cluster instability for a while. And even the solution we sort of converged on won't be able to scale indefinitely as their data size grows. So what are the challenges with doing this? Well, these two systems are very different. Cassandra is distributed. Different nodes own different portions of the data. It's eventually consistent, so different nodes may see slightly different views of the data for some potentially large amount of time. Updates are partial. They're not full rows. They can be any subset of columns. And there's data replication, which means you have a number of replicas which themselves may see slightly different ordering of the writes to different keys. And to that, we're trying to go into Kafka, and specifically Kafka in our data pipeline, in which you have a total ordering of events by key. Each message has the full row. It has the previous value in the case where it's an update or a delete, and it's nearly exactly once publishing. So this is the very high-level overview of the system we created. It consists of mainly two pieces. The first one is designed to stream the writes out of Cassandra into an intermediate Kafka topic, and then another piece that takes this global change log and uses stateful stream processing to turn it into the final message format that we need to publish to our data pipeline. So I'm going to be talking about the first piece of this, the process of getting the writes out of Cassandra into an intermediate topic. This is a very simple view of the Cassandra node write path. Client write comes in, gets persisted to the commit log, gets loaded into the mem table. Eventually, the mem table gets big, gets flushed to disk as an SS table. One thing to note here is that the commit log itself isn't just one giant file. It's actually made up of a bunch of smaller files called commit log segments. These are fixed size, default to 32 megabytes. When one fills up, it allocates and moves on to the next one. So how did we decide to get writes out of Cassandra? We decided to leverage change data capture, or CDC. This was a feature added in the later 3 series. It can be enabled on both the node and table level, which means you can enable it on both a subset of nodes and for a subset of tables. And its main function is to allow a way to process the writes to a Cassandra node for the tables you want tracked. And it does this by exposing commit log segments as they're discarded. So what does that look like? This is how it fits into the write path. The commit log gets all the writes as they come in. Eventually, the segments get full. At some point, it needs to get rid of them. And so in CDC, rather than deleting the segment, if it has data for a table you're looking at, it moves that segment into a special folder to allow you to process it later. There are 2 conditions that need to be met for this to happen. First of all, this segment has to be full. It can't be the live segment that's currently being written to. And second, there can't be any mem tables left that are referencing data in that segment. And this is because if there's a crash, this commit log segment needs to be used to reconstruct the current mem table. So obviously this kind of has some drawbacks. The latency is poorly bounded. And when I say that, I mean the latency of how long it takes to write to the cluster and have it appear for processing. This is because the segment must be full and the mem tables must be flushed. This must be processed per node. There's no global replication stream, so you end up with a bunch of individual streams you need to process. You got to process writes on each replica, and so this guarantees you're processing the same write at least a replication factor number of times. These writes also only contain the data the client wrote, nothing about previous value, nothing about other pieces of the row value. And there's no tracking of schema changes. And in fact, you have to manage metadata in Cassandra's format in order to be able to process these segments. So really, to make this useful, we kind of had to bound the CDC latency somehow. We did this by first deploying a virtual data center on our cluster. This would have the key spaces we were interested replicated into it. It would just essentially be taking writes. It wouldn't be taking client reads. And because of that, we've isolated the performance of our clients. It also means we get to provision it a little differently because we don't have to provision it for writes. It really just, or reads, we just have to provision it for the writes and sort of the additional compaction load and whatever our tooling's doing. So to solve the mem table referencing problem, we have periodic flushes that happen on these nodes to make sure that within a given amount of time, the current segments won't have any mem tables that reference them. And then for the case where a table is being written to very slowly, we have a sort of filler key space that we deploy just in this virtual data center with a very steady computed write rate to make sure that we can guarantee that these segments will be full within a given amount of time. And so using these strategies, we currently have our production cluster bound at a 10-minute maximum latency. It's a little arbitrary. And it can actually be less depending on the write rate of the cluster, but that's the maximum upper bound. So how does CDC processing work? You have to implement a commit log reader handler. This is an interface that's provided in Cassandra that allows you to do custom processing of each mutation within the commit log segment. Using this, you use the provided commit log reader, and it just processes through whatever segment you give it. A mutation is the Java object in Cassandra that essentially represents the table data. And it's, in this case, this would be the write that the client made to the cluster. So a little bit more detail on it. So a mutation contains a set of partition updates for a number of tables. And a partition update is just data for a single Cassandra partition key, which contains things like deletion information and a number of data rows. And then the rows are the data values for a clustering value in that partition, which has columns which have either data or tombstones and timestamps. This is a very simplified view. It doesn't contain everything, but mutations contain partition updates, which contain rows, is really what you should take away from it. So we built ourselves a CDC publisher. It's just a local Scala service deployed on the CDC-enabled nodes. It watches the CDC raw folder for new files, and as they're moved, it processes them in order. Its primary job is to break up the mutations. So it breaks them into their individual partition updates, and in the case where those updates have multiple rows, it breaks them into individual updates with single rows to allow for simpler processing downstream. Once we have these updates, we need to serialize them somehow. These are Cassandra data objects, so we just use Cassandra's serializers. They're versioned and well-defined. And so we end up with the serialized data, and now we just want to publish this to Kafka. We publish it to a per table topic. It has the data, it has a couple of metadata fields, mainly for auditing, and then it has the Cassandra messaging version to make sure that we know how to serialize it later. To ensure it's scalable, you can add multiple partitions to this topic. You just have to make sure that you're partitioning your topic by the Cassandra partition key, to make sure updates to the same key end up in the same Kafka partition. This ensures that there's a deterministic order to process them later. As I alluded to before, you have to do a little managing of Cassandra metadata. You need to do this to use Cassandra functionality that interacts with binary data. You need to initialize their schema objects, the main one being the CF metadata, which stands for column family metadata. It's essentially just the description of the table, what columns are in it, what their types are, table properties, what are the keys, that kind of stuff. So it's needed to do the CDC processing, and it's also needed to do any serialization and deserialization and partition updates. One way it can be loaded is the system tables have this information, and you can initialize your schema from the local system SS tables. This is good. It's pretty easy, but it only works if you're on the Cassandra node, which this part is, but the second part of our system isn't. And we also ran into issues trying to detect and reload the schema if there was a schema change on the cluster. So to deal with that, we created sort of a remote way of building the schema metadata. We use just the driver to connect to the Cassandra cluster. The driver pulls down the metadata. So from the driver, we can get the create statements for the types and the tables that we're interested in. And then since Cassandra is a dependency of this already for CDC, we just use its own query processor to parse the create statement and build the CF metadata object. The one thing we did need to add was dropped columns aren't pulled in as metadata. This is the metadata for when you drop a column. It says the name, it says the type, it says the time. This is really important because if you don't have this initialized correctly and someone drops a column, you won't be able to read updates that have that column. And the other thing we did is we registered a schema change listener so that this class gets a notification whenever the driver detects a metadata change. And if it's one we care about, we set a flag and we make sure to check that before we process each new segment. And if it changed, we rebuild our metadata. And the last thing I'm going to touch on is backfilling data. This is if you need to publish all the data that exists for a table into this pipeline. You need to do this if you were, say, trying to add a table that already existed into this infrastructure, or if for some reason you had to rebuild the downstream state. For this, we just use Cassandra's SS table reader to scan through the SS tables that we need. This reader brings back data as partition updates, which is exactly the same thing we're processing in the real-time pipeline. So we treat them exactly the same way. We break them up and we publish them to the exact same table topic. And to ensure that we don't have any issues with compaction, we take a node tool snapshot first and we publish off those tables rather than using the live tables. So where we are so far, we have a local service that's running on each CDC-enabled node in a virtual data center. It's publishing all the commit log entries for the tables we care about into per table Kafka topics. It essentially has a unified commit log for the cluster for that table. And it sets a total ordering of updates to process by key. This isn't exactly what we need. It's not necessarily in write time order, so the last update for a key may not necessarily be its final value. It'll definitely contain duplicates based on the replication factor. It's partial updates, not full rows, and there's no information about previous values. So it's the job of the second part of the system to resolve this problem.
Thanks, Andrew. So what we have so far is an upstream Kafka topic, which you see on your left with a series of partial partition updates. And the goal is to convert those series of partial partition update into series of complete data pipeline messages is what we need. We're going to achieve that with the help of this centerpiece, which we're calling stateful stream processor. It's an application built on top of Apache Flink. So first, for folks who are new with Flink, Flink is nothing but a complex event processing system. It takes in a topology of code and knows how to execute it in a distributed fashion. For folks familiar with Spark or Hadoop, it's kind of in that space, but those frameworks take a more batching first approach, whereas Apache Flink takes a streaming first approach, which is ideal for the kind of application we are trying to build. Some of the properties of Flink, which are key to building this application, are ability to do stream processing. Flink provides reading and writing to Kafka out of the box, which is exactly what we need here. It has support for inherent state, wherein application state can be offloaded and reloaded from persistent database like RocksDB. That is the second thing that we need. Flink provides an ability to do checkpointing, which ensures fault tolerance in the application. What that means is the positions of data in upstream and downstream Kafka are always guaranteed to be in consistent state with the runtime state of the application. Flink provides an ability to do save pointing, which ensures that we can safely pause and resume our application without having to worry about over-processing or under-processing any data. The stateful stream processor, which is built using Apache Flink, has two main phases in the application. The bootstrap phase is what generates the Avro schema from the CF metadata object that Andrew was talking about. And in the runtime phase is where we read those series of partial partition updates, transform them into complete data pipeline messages using inherent RocksDB state, and finally publish those complete data pipeline messages into downstream Kafka using the Kafka producer. Let's understand all of those parts in detail. In the schema generation phase, we basically take the CF metadata object and parse that into Avro schema. Avro is a data serialization protocol similar to protobuf, which takes in an Avro schema JSON and a data JSON and knows how to convert that into a byte array. I highly encourage you to go check out the Apache Avro project for more details. Once we have the Avro schema generated from the CF metadata object, we enrich that schema with two key pieces of information. The first one being primary key. Primary key is a composition of the partitioning key and the clustering key available on the Cassandra table. This is important because we want our Kafka streams to be keyed and not arbitrary. The second point being all the columns which are not the partitioning key and the clustering keys, that means all the fields within the Avro schema that are not primary keys are nullable by default and have a default value of null. What this means is, this is particularly important so that as the Cassandra table undergoes schema changes over time, the resulting Avro schema that gets generated needs to be backwards and forwards compatible as the system evolves over time. So second point is for that. And overall, the system is capable enough of detecting changes in the Cassandra table schema based on the mechanism, the remote metadata loading mechanism that Andrew described before. We're able to detect the change in the Cassandra schema and generate the resultant Avro schema, which is used in the following sections. For example, on the top, you can see a sample create table statement on Cassandra. And at the bottom is what is an example CF metadata object as represented in Cassandra's runtime. The important things to note here is that the CF metadata object encompasses all of the key pieces of information that are described in the create table statement, like key space name, table name, the two fields, out of which one is a primary key. So the goal of the schema generation phase is to take that CF metadata object and create this. This is the Avro schema corresponding to that CF metadata object, which also contains the same level of details. I want to get your attention to the two pieces of data that we overlay on top of the base schema. That is the primary key, which is as indicated in the CF metadata object, and the non-primary key field has a default value of null.
Your favorite movies and TV are on YouTube. Press play on something new.
Are there any gay hockey players?
Cool. Now that we have a way to generate the Avro schema, let's focus our attention.
Okay, so I think we can have enough information to write down. So I guess one other source of database self-use is Cassandra. Out into close up Cassandra CDC data capture. Write to Kafka. Wait, in the V3 I guess this have the schematizer, right? Okay. To publish to data pipeline, it needs to schema, register, schematizer. It was done with DP materializer. So I guess Cassandra know the exact column, specific column. No, well, column. So it is. Okay, I think that should be fine. More information. Once again, shuffling up. Guess version at this point. Wait, no, this is part 2. Okay, I think we're done the L part. Think gonna take some break, maybe play some games. That's it for the study today.